topic of my presentation is secure deduplication of encrypted data. The title of the paper I selected is Secure Deduplication of Encrypted Data Without Additional Servers, and the authors are listed below. You can find the scripts of my presentation in the remark of these slides. Here is the table of the contents of my slides. Firstly, I will give a brief introduction to data deduplication and PAKE. And next, I will introduce the challenges of deduplication on encrypted data, and then the methods proposed by the paper, as well as the evaluation of the proposed methods. Also, I will give the advantages and the contributions of the method, and the challenges and the future improvements. Finally, I will give the conclusion. Firstly, I'm going to introduce data deduplication technology to give a clear overview. Data deduplication technology is a process that eliminates redundant data from a storage system. It is a technique that identifies and removes duplicate data blocks, resulting in significant storage space savings and improved data management. The technology is widely used in enterprise storage systems, backup and recovery solutions, and cloud storage services to optimize storage utilization and reduce costs. In general, data deduplication works by identifying and removing redundant data blocks from a storage system. It uses algorithms to compare incoming data with existing data blocks and identifies duplicates. Once identified, the duplicated data blocks are replaced with a reference to the original block, and resulting in significant storage space savings. The process can be performed at various levels, including file, block, and byte level, depending on the storage system and the data type. File level deduplication usually uses some hash functions to generate a long hash of the entire file. The server identifies identical files by comparing these hash values. It is adopted by this paper. Usually, file level deduplication has minimal cost and the worst deduplication effectiveness compared with block level and byte level deduplication. Block level deduplication divides a file into several file blocks, use some specific algorithms. The system will generate a recipe for the file. The recipe includes the file blocks it contains and their order. When the system needs to reconstruct this file, the system will fetch this recipe and retrieve related file blocks. Byte-level deduplication is similar to block-level deduplication, but it divides a file into much smaller file blocks in byte level. Hence, it could achieve the best deduplication effectiveness and require a huge amount of computation. Data deduplication can also be categorized by when the deduplication is performed, including inline, post-process, and concurrent deduplication. Post-process deduplication is performed after data has been written to the storage system. It is less efficient than inline deduplication, as it requires additional storage space to hold the data before it is deduplicated. However, it is less resource intensive and can be performed during off-peak hours. Inline deduplication is performed in real time as data is being written to the storage system. It is the most efficient form of data deduplication as it eliminates redundant data before it is written to the storage system. This reduces the amount of storage space required and improves data transfer speeds. Concurrent deduplication is a hybrid approach that combines inline and post-process deduplication. It performs inline deduplication in idle time and post-process deduplication in peak hours. This ensures that data is deduplicated efficiently while minimizing the impact on the storage system performance. The benefits of data deduplication technology are numerous. Firstly, it reduces the amount of storage space required for data storage. This is particularly important in enterprise storage systems, where the amount of data being stored can be enormous. By eliminating redundant data, the storage space required can be reduced by up to 90%, resulting in significant cost savings. Secondly, data deduplication technology improves data management. By eliminating redundant data, it reduces the amount of data that needs to be backed up, replicated, or migrated. This reduces the time and resources required for data management tasks, resulting in improved efficiency and productivity. Thirdly, data deduplication technology improves data protection. By reducing the amount of data that needs to be backed up, it reduces the backup window and improves recovery times. This ensures that critical data is protected and can be restored quickly in case of disaster or data loss event. Also, data is separated and stored independently, making it hard to reconstruct the original files for an attacker. Fourthly, data deduplication technology improves data transfer speeds. By reducing the amount of data that needs to be transferred, it improves data transfer speed, particularly over networks with limited bandwidth. This ensures that data can be transferred quickly and efficiently, even in remote locations. In conclusion, data deduplication technology is a powerful tool for optimizing storage utilization and reducing costs. As data volumes continue to grow, data deduplication technology will become increasingly important in managing and protecting critical data. However, everything changes when the data is encrypted. Here I will introduce the general challenge of deduplication on encrypted data. Just imagine such a scenario. There is a plain text 123. After being encrypted with two different keys, the ciphertext becomes 456 and 789. The ciphertexts are not identical, but the client uploads the plain text to the cloud. The cloud just needs to store one copy, but after being encrypted, the cloud needs to store two copies. The cloud server cannot identify the same files after they are encrypted. It is a prominent challenge for deduplication on encrypted data. Here come two solutions. One of them is to send the ciphertext along with the encryption key to the server. It is dangerous and loses the meaning of encryption. Also, it is expensive as it imposes high demands on computing resources. The other one is to use the same encryption key to encrypt the same file, and hence the ciphertext will be the same, and makes it much easier for the server to perform data deduplication. Also, this method is cheaper as most computation is conducted on the client side, but there is a challenge waiting for us: how to share the encryption key among the clients who own the same file. This paper solves the challenge of deduplication by using the second method. Details will be given later. Here I will briefly introduce PAKE. PAKE is short for Password Authenticated Key Exchange. It is a cryptographic protocol that enables two parties to establish a shared secret key using a password as the only input. The protocol is designed to provide secure authentication and key exchange without the need for pre-shared keys or public key infrastructure. In a typical PAKE protocol, two parties, such as Alice and Bob, agree on a password beforehand. During the protocol execution, they exchange messages to establish a shared secret key that can be used for subsequent communication. The protocol is designed in such a way that an attacker who intercepts the messages cannot learn the password or the shared secret key. PAKE protocols are based on the concept of zero-knowledge proofs, which allow one party to prove to another that they know a particular secret without revealing the secret itself. One of the main limitations of PAKE protocols is that they are vulnerable to dictionary attacks. In a dictionary attack, an attacker tries to guess the password by trying a large number of possible passwords until they find the correct one. PAKE protocols can be made more resistant to dictionary attacks by using techniques such as sorting and stretching, which makes it more difficult for attackers to guess the password. Another limitation of PAKE protocols is that they are vulnerable to man-in-the-middle attack. In a man-in-the-middle attack, an attacker intercepts the messages exchanged during the protocol execution and modifies them to redirect the communication to a different party. PAKE protocols can be made more resistant to man-in-the-middle attacks by using techniques such as MAC and digital signatures to verify the integrity and the authenticity of the messages. PAKE protocols have been widely used in various applications, including online banking and secure messaging. For example, in online banking, PAKE protocols are used to authenticate users and establish secure communication channels between users and the bank's servers. Here is the PAKE protocol used in the method proposed in this paper. One client, Alice, runs multiple PAKE instances with other clients. If Alice uses the same password with one other client, they will have the same output. In the method proposed by this paper, it uses the hash value of the file as the password. If two clients have the same file, they will have the same password, hence they can use the PAKE protocol to communicate safely. Now, let's look into the details of the proposed method. In case 1, client A uploads a unique file to the server, though other clients have the same file. Firstly, it will generate a short hash of the file as the identity of the file and then send this short hash to the server in the second step. In the third step, the server compiles the hash with all the existing short hash it has. If it cannot find one that is identical to the hash it received, it will generate a random encryption key to client A. The client A will use the key it receives to encrypt its file and send the ciphertext to the server for storage. In case 2, client A uploads a duplicate file to the server. There exists some clients owning the same file. Firstly, client A will generate a short hash of the file as the identity of the file, and then send this short hash to the server in the second step. In the third step, the server compares the hash with all the existing hash, and it will find several clients owning the same short hash. Due to hash collision, those clients who have the same short hash may not have the same file. In the fourth step, the server will use some approaches to find a client B who has the same file as client A. Afterward, the server and the two clients will run PAKE protocol to exchange the encryption key. Then the client A will use the same key as client B to encrypt the file. Finally, client A will send encrypted file to the server for storage. In the previous slide, I mentioned that the server will use shorthash to find potential clients who may have the same file as client A and use some other approaches to finally distinguish the client who actually have the same file as client A. Here I am going to introduce the approach in detail. In step 1, client C generates short hash and the server uses the short hash to filter out all the potential clients. Let's say C1, C2 to CI. Client C is the uploader, while client C1, C2, CI are the checker. In step 2, client C generates a long hash from its file. Client C1, C2 to CI generates their own long hash as well. We need to notice that if the long hash is identical, the original file is identical. In the next step, each client CI splits its long hash into two parts, L and R. Compose its own key with R, and then send LR along with its key to the server. For client C, it also splits its long hash into L prime and R prime. It will also generate a random number R and encrypt R prime and small r. Finally, client C sends L prime and the ciphertext to the server. In the fourth step, the server will find the identical L and L prime, hence the server will know which client shares the same file as client C. Let's say client J shares the same file as client C. Afterward, the server will encrypt the R and the key of the client J and subtract it with the ciphertext from client C. The result is E. We can see that E equals to the encryption of the difference of key and R, and then the server sends E to client C. In the fifth step, the client decrypts E and gets the key of client J. Now client C and client J share the same encryption key, and the server does not know the key. Client C uses this key to encrypt its file and send the ciphertext to the server. If the ciphertext is unique, store the ciphertext, else the file is duplicate. Give client C the access to the file which has been stored already. The procedure is complex. You may stop here to investigate the procedure above. I think the figure above may solve some of your confusion. Here I'm going to introduce the defense adopted by this paper. When using hash value as the identity of the file, it is possible for an attacker to guess the content of the file by applying brute force attack. Therefore, to check the existence of one particular file, the client will send short hash instead of long hash to the server for investigation, as short hash has larger probability of hash collision, hence preventing offline brute force attack. From observation, in a large-scale system, a short hash matches many files. limited information about the uploaded file is leaked. In the real world, it is possible for an attacker to compromise the server and mount an online brute force attack, while it initiates many interactions with the clients to guess the content of the files. To prevent such kinds of attacks, each interaction between the server and the client essentially enables a single guess about the content of the target file. Clients therefore use a per-file rate limiting strategy to prevent such attacks. Specifically, they set a bound on the maximum number of PAK protocols they would serve as a checker or an uploader for each file, hence making such attacks extremely time-consuming and easy to be detected. When there are not enough checkers, it is possible for the attacker to apply brute force to know which client owns this file. Generally, if the server has a large number of clients, it is likely to find enough online checkers who have uploaded files with the required short hash. It would take the attacker a large amount of time to investigate each checker. If there are not enough checkers, the method can let the uploader run PAK with the currently available checkers and with additional dummy checkers to hide the real number of available checkers. Hence the information leaked is highly limited. Next, I will introduce the challenges that this method is facing and propose some possible improvements. In general, there are 3 points in total: limited data sets, support block-level deduplication, and symmetric encryption of small files on the server side. First of all, limited data sets. Deduplication effectiveness is highly dependent on the data size. As I can see from the paper, the dataset is limited. It is obvious that file-level deduplication has a better performance on system backup because most files are identical across different system backups. When facing data from social network, most personal photos, videos are not identical, which will decrease the deduplication effectiveness. The authors claim that their method achieves good performance in their data sets. However, in my opinion, analysis using more realistic data sets is necessary. The next one is to support block-level deduplication. This method generally applies to file-level deduplication, which means it can only detect totally identical files. For example, user A uploads file A to the cloud, and then user B slightly changes file A into file B, and upload file B to the cloud. File A and file B are highly similar, but will be regarded as two different files and stored independently. One approach to handle this issue is block-level deduplication. To be more specific, block-level deduplication divides the file into several data blocks, and the client uploads these blocks to the cloud. While this may significantly increase the overhead of key exchanging, as stated by the paper, from my experience, for the best storage efficiency, current deduplication solutions usually divide the file into blocks of size around 4 kilobytes, which means that a 1 megabytes file will generate around 250 encryption keys and run the PAK protocol 150 times, which dramatically increases the demands on computation and network resources. It would be a great challenge to support block-level deduplication in this scheme. Here is the benchmark result from the paper. As we can see from the figure above, it reports the uploading time and bandwidth usage in the protocol compared to the two baselines, plain files and encrypted files. For files that are smaller than 1 megabyte, the overhead introduced by the deduplication protocol is relatively high. For example, it takes 15 milliseconds to upload a 1 kilobyte encrypted file, while it takes 319 milliseconds to upload the same file. However, the overhead introduced by the deduplication protocol is independent of the file size and becomes negligible when the file is large enough. For files that are larger than 64 megabytes, the time overhead is below 2%, and the bandwidth overhead is below 0.2%. Therefore, the last improvement I propose is to use symmetric encryption to handle small files on the server side. As we can see in the test result, when storing small files, it takes more than 10 times time compared to storing plain files. When it comes to storing numerous small files, it would be extremely time-consuming. One possible way to handle this issue is to upload the files with TLS or SSL. After receiving these files, the server encrypts these files and performs deduplication. To be more specific, set a file size threshold like 1 megabyte for the files which are smaller than 1 megabyte. The server performs symmetric encryption on the server side. For those files which are larger than 1 megabyte, use the method proposed by this paper. Such threshold will significantly decrease the time storing small files for sure. While this method requires the server to protect the symmetric key, and hence the server cannot be compromised by the attacker, and must be resilient to brute force attack, which imposes a high demand on cybersecurity. Meanwhile, this method can also apply to insensitive files for better user experience. In conclusion, this paper proposes the first secure and efficient deduplication scheme for encrypted data without the need for additional independent servers. The scheme uses homomorphic encryption to enable the server to perform deduplication operations on encrypted data without accessing the plain text. The scheme provides several security guarantees and efficiency improvements, and was shown to be efficient and secure through simulations and experiments. The proposed scheme has potential applications in cloud storage services and other data storage systems where secure deduplication of encrypted data is required. Also, the scheme has no computational and communication overhead compared to existing solutions. However, there is still space for future improvements, such as supporting block-level deduplication for better deduplication effectiveness. Also, it can use symmetric encryption to handle numerous small files and insensitive files. Thank you. That's all.